All right, so hello, everybody. Welcome to the foundation session. I'm Juan Garay. I'm guest chairing this session. And let's start with low entropy requirements. Let me get this out of the way. With low entropy requirements colliding with no malleability, this is joint work by Divesh Agarwal, Eldon Chang, and Maciek Obremski. And Maciek is giving the talk.
Yep, thank you. So yeah, it's our joint work with Divesh, Eldon, our student, and me. It works. So there are random processes around us, and some of them are better than the others. And intuitive kind of understanding of which process is more random than the other is quantified in our world with the notion of entropy. There's plenty of variants. The one variant we are interested in cryptography is the notion of mean entropy. So we have some random variable. We look at what's the most probable outcome. We take that probability and we minus log it. So if the process is deterministic, the probability is 1 minus log is 0. So deterministic processes have mean entropy 0. On the other hand, if we look at something that's uniform over n-bit strings, the mean entropy is n. And notice that this n is the maximum possible, so we can start thinking about entropy rate. Entropy rate will be the ratio of mean entropy to the length of the string, right? So if the random variable has n½ mean entropy and length n, the ratio is half. So once we figured out how to quantify the quality of random sources, the natural question is, can we turn a random source, like low quality, into better quality random sources, right? And this is formalized by the notion of extractors. So extractor will be a deterministic important function that takes something with some amount of entropy, mean entropy, and output something with more mean entropy, or preferably something indistinguishable from uniform. And sadly, this cannot exist unless we assume something about the structure of the source. So the second best thing we can do is get two sources. So we get two sources, each of them is independent of each other, they have some amount of entropy, and then there exists a deterministic function that will take those two sources and output something uniform, okay? On top of that, we can ask for extra properties, namely non-malleability. So non-malleable extractors are standard extractors, so they take two sources, each source has some entropy, they will output something uniform, and on top of that, they have an extra property. If we look at x prime, that's correlated to x, and y prime, that's correlated to y, and that correlation can be due to various reasons. Maybe it's a result of some physical processes, maybe it's a result of adversarial tampering. And then we plug it in this correlated randomness into extractor, we get output prime. And non-malleability guarantees that the original output remains uniform, even given output prime, right? So to reiterate, even if x and x prime are correlated and y prime are correlated, the non-malleable extractor breaks that correlation, right? The outputs will become independent. Obviously, this can only happen if either x prime is different than x or y prime is different than y, because if those are identical, then the output will be identical. Right, so non-malleable extractors, as long as they see something different, the output is guaranteed to be independent. So they break any kind of correlations. Okay, what do we know in case of a negligible error? So the extractors that are used in crypto. We have RAS extractor. RAS extractor requires one source to have mean entropy rate half, and the other source that's polynomial entropy. But that one is not non-malleable. If you see output on some correlated sources, the output might be correlated. Then we have a class of seeded extractors, seeded non-malleable extractors. one source has polylogarithmic entropy, the other is uniform, but very short. And those are, the uniform one is called seed. And those are non-malleable, but only with respect to the seed. So if you see the output on the same random source, but correlated seed, this extractor is capable of breaking this correlation. And then finally, we have fully non-malleable two-source extractors, so two-source non-malleable extractors. This is the definition I just gave. But the problem is they require both sources to have almost full entropy. 0.99 is a placeholder, just exists a constant slightly less than 1. Okay. And what we do is we build two-source non-malleable extractors, so fully non-malleable, and we lower the entropy requirements. So we lower the entropy of one source from 0.99 to 0.8, which is like, you know, big difference. It's suddenly reasonable entropy gap. And the other source is even better. It goes all the way to polylog. So in a sense, it's a best of all worlds. If you look at two-source non-malleable extractors, well, we completely destroyed their requirements here. Our requirements are very low. If you look at seeded non-malleable extractors, first of all, we get full non-malleability with respect to both sources. Second of all, this does not have to be uniform. It can be 0.8. And finally, if you look at RAS extractor, we sacrifice a little bit of entropy. We go from entropy rate half to entropy rate 0.8, but we gain full non-malleability. A little bit of history. Goyal, Srinivasan, and Zhu in 2021 considered following transform. They are building almost two-source non-malleable extractor. It has two sources. One is X, and the other source is split. The prefix is Y1, the suffix is Y2. And what they do is Li, I'll explain what's Li. Li is a two-source extractor. One input to Li is Y2, and the other input to Li will be some other extractor on X and the prefix of this source. Okay, those are the building blocks. Li is this two-source non-malleable extractor, nicely fully non-malleable, but requires very high entropy rates. C is just seeded extractor. It has no non-malleability property. One source has to be uniform, almost. The other source can be polylogarithmic. And what they build is their extractor requires one source to have polylogarithmic entropy. The other source has to be uniform. And yeah, if you plug it in, if this is uniform, then Y1 is uniform. This is sufficient to run the seeded extractor. So this is uniform. And now, since this was uniform, Y2 is also uniform. This is sufficient to run Li. Everything is nicely uniform. There is a small issue. C has no non-malleability property. So if you can find X prime and Y1 prime, such that, well, they are different than the originals, but the output of the C extractor stays the same, then, well, Li will not see any difference, right? Li will see Y2, and here he will see the output, which is the same. So the output prime will be equal to output. So they don't get full non-malleability, they get a weaker notion. It's sufficient for their application to network extraction, but it's not sufficient to all applications. So this is like a weaker version of non-malleable extractor. As a side note, this has to be uniform because both Y1 has to be uniform and Y2 has to be close to uniform. So if you do these tricks with cutting sources into prefixes and suffixes, like you kind of have to work with this. Okay, so we take this transform and we look at it with a few twists. The first twist is E is a placeholder, think of Li. This looks exactly the same, but now we add this. It's slightly counterintuitive because now suddenly we have Y1 here and Y1 here, and those two sources have to be independent, but there are technical ways of dealing with it. It's not a big problem. But now look at what happened in the previous slide. We had this problem of, hey, if this is equal, then we have a problem, the output stays the same. But now notice that this E, that's two-source non-malleable extractor, sees Y1 in the open. So if Y1 changes, the definition of two-source non-malleable extractor guarantees that the moment two-source non-malleable extractor sees any difference, it will output something independent, right? So in this case, this extractor will output something independent. So the problem reduces to this problem. What if I can produce X and X prime that are correlated but not equal, such that the output of the extractor stays the same? And that's great because that's collision resistance, right? If we're talking about collision resistance, we have to talk about leftover hash lemma. Leftover hash lemma basically says that if for every x0, x1 not equal, probability over uniformly chosen Y, probability of collision is tiny, then C is a good extractor. Good. With Skursky, we showed that inverse is also basically almost true, like every good every extractor has a core on which it is collision resilient. So we know that, kind of morally speaking, the extractors and collision resilient objects are kind of equivalent, modulo some pathological cases that force us to looking onto like the core of the extractor in a sense, but there are only some pathological cases which spoil it. So let's define a role model extractor, the extractor that we would like to see according to LHL. So the extractor has to extract. So if the sources have some entropy, the output will be uniform. And on top of that, we require collision resistance. So we require that if I look at X and X prime that are arbitrarily correlated but not equal, the probability of collision is tiny. And this probability can be taken over Y and over X, which makes it even easier, right? So the natural question is, what's collision resilient? All seeded extractors, so the extractors that have one source polylogarithmic and the other uniform, there's no non-malleability guarantee here. All seeded extractors either are collision resilient straight out of the box, or they can be compiled. Also, Razes extractor, so this extractor that has one source with entropy rate half and the other source with polylogarithmic entropy, also is collision resilient if you play a little bit with the parameters. Okay, so our construction, we take basically this slightly updated GSZ transform, and we compile Lie and Trevisan. Okay, what happens if we compile Lie and Trevisan? I'll say what's Lie and Trevisan in a second. We will be building basically what GSZ built, but now it's gonna be fully non-malleable. So like not the weak non-malleability, but like full proper two-source non-malleable extractor. One source will have polylogarithmic entropy, the other source will be uniform. That means that, well, Y1 is uniform, X is polylogarithmic entropy. Trevisan is a seeded extractor that's collision resilient. So if we plug it in, that's sufficient to extract. This is uniform. And now this is uniform. This was uniform. This is basically almost uniform, modulo some technicalities. That's sufficient to run Lie. Okay. You should think about it in a way of Lie gives non-malleability, and whatever you have here gives lower entropy requirements. So we have a first step in the construction. We constructed two-source non-malleable extractor with full standard definition that has polylogarithmic entropy in one source and uniform entropy in the other. Okay, now we will take this and compile again. So now we will compile it with Ras extractor. One source will be polylogarithmic, the other will have entropy rate 0.8. And if we play with entropy rate and we play with suffixes, prefixes, we choose the cut accordingly, we can guarantee that Y1 will have entropy rate at least half. Right? That's why this 0.8 pops up here. Okay, if Y1 has entropy rate at least half, that's sufficient to run Ras. Okay, that's uniform. And now there are small issues. The entropy of this dropped significantly because, in a sense, entropy of Y1 has been used up. In a previous step, that wasn't an issue because Y1 was very short. It was just a seeded extractor, which is super short. But now, because we have to cut it in a kind of more complicated way, this entropy is significantly smaller than entropy of this. But that's not a problem because our FNMX requires one source to be uniform, but the other can have polylogarithmic entropy. So we only have to play with parameters to guarantee that this has just tiny amount of entropy left after the whole proof. And again, think of NMX as giving non-malleability, and RAS allows for lower entropy. So the final result is as follows. We get two source non-malleable extractor, one source entropy 0.8, entropy rate, the other source polylogarithmic. We can also tolerate multiple tamperings. So multiple tamperings, it basically means that instead of seeing the output on one correlated set of sources, inputs, you can see on multiple, right? You pick multiple correlated inputs, you see the output on each of them, and the original output remains uniform and independent, right? So this extractor is capable of breaking way more correlations. And the entropy rate requirements is one source polylogarithmic that stays. This entropy is 1 minus 1 over 2t plus 3. If you plug in t equal 1, you get this. It will be important at the end of the talk, but I'll remind you the formula. Was it me? Sorry. In subsequent work, Lee gave a construction of two-source non-malleable extractor. So he lowered the entropy of one sources from 0.8 to 2 over 3. Okay, but that's only for single tamper. Okay, why care? So one reason to care is because two-source non-malleable extractors are cool tools. They can be used for multiple purposes: privacy amplification, network extraction, non-malleable codes, leakage resilience, tamper resilience, secret, non-malleable secret sharing, and so on. And I'll focus on privacy amplification. So what's the privacy amplification setting? As Alice and Bob share a secret, but the secret is not uniform. They used it up in a previous communication, something happened, whatever. The secret is only guaranteed to have some mean entropy. Now, they would like to engage in a protocol, and at the end of the protocol, they would like to have shared uniform randomness. So they would like to upgrade this W to something uniform. Okay, that's kind of trivial. I can just send you something uniform. So obviously, to make it slightly more complicated, there's Eve in the middle. And Eve not only eavesdrops, for that we could just use seeded extractors, but also tampers with the channels. So Eve has full control over channels. We don't trust them. And in the end, it's still guaranteed that either Alice and Bob will derive something uniform and secret to Eve, like Eve will not know what it is, or at least one of them will abort. For this setting, all you need is seeded non-malleable extractors. You don't need full two-source non-malleable extractors, but you can imagine more complicated setting. Imagine a stronger variant, one of Alice or Bob, it's symmetrical protocol. One of them is a smart card, right? So they still share this W, and there is Eve that controls the channels, but because one of them is a smart card, he does not really have access to randomness. So Eve, on top of controlling the channels, can control the randomness. And on top of that, we can allow Eve to tamper with the smart card and derive some tamper with W to W prime. Eve can even leak a little bit about original W. So even in this very strong adversarial setting, we can guarantee, using two-source non-malleable extractors, that either Alice and Bob will agree on uniform randomness that's unknown to Eve, or at least one of them will abort. So it's extremely strong tool that allows even in such a lost cause to derive something uniform. So why do I care mostly? There's this cool problem of building two-source extractors. So we talked about two-source extractors. Now think about both sources having the same entropy, right? And we're looking at the entropy rate that's required. Both sources have the same entropy, right? So we have known for a very long time that if both sources have entropy rate above half, the inner product is a good extractor. And then there was an open problem for a very long time to go with both sources below half. So this is not the case of RAS. RAS gets one source below half, but the other still has to be above half. The problem was, can you get both sources below half? And Burgain in 2005, showed that it is indeed possible. And he gave a construction that goes with both sources slightly below half. Then in 2019, Levko gave a improved analysis of Burgain with the latest results in additive combinatorics and gave the construction with 4/9. Okay. On the other hand, we've got CZ14 that works with logarithmic entropies. The question is, why aren't we done if we have, extracted that works with logarithmic entropies? The problem is that it has 1/poly error. And even if I give you way more entropy, the error stays 1/poly, so it's kind of not suitable for crypto. Which leaves us with like huge range of parameters in which we know that probabilistically there exist extractors, there exist non-malleable extractors, everything cool exists in that region, but we can't construct anything. I'm not even talking about non-malleable two-source extractor. I just want two-source extractor, standard version, and we don't know how to construct it. So there's a lot of connections between seeded non-malleable extractors, two-source extractors, and two-source non-malleable extractors. And in particular, we know that if we could construct two-source non-malleable extractor with entropy threshold 1 - 1/t, where t is number of tamperings, or number of correlated sources, then we could get two-source extractors in a huge range of parameters that would imply all the cool stuff. We would get better two-source non-malleable extractors, like everything would be great. And this paper gets 1 - 1/2t, which is not quite the threshold, but I mean, it's the first paper that even gets close to linear dependency in the denominator. Okay. I hope you're equally excited about this, and thank you.
Thanks, Maciek. Any questions? So that's the main goal that you have, future research type thing, improving your bound.
Sorry?
What future research, open questions? That's the main, what you just showed.
So the one question would be, can we get this entropy slightly lower? And yeah, it's possible to use other objects than just extractors and build their collision resilient option. Like you can see that like all we need is basically condensers to some extent. So if we could build condensers that are collision resilient, this is not very exploited approach. Just build a better collision resilient object. If we can do that, then hopefully we can break through this 1 - 1/t barrier. So that's kind of the goal.
All right, any other questions? If not, let's thank Maciek again. And we're moving on to the next talk. Oh, so by the way, there is some merchandise left. So I guess feel free to stop by, pick up, except that you have to leave one extra large, windbreaker, because I didn't pick up mine. All right, so Where do I see it on Zoom? Next talk is PAC privacy, automatic privacy measurement and control of data processing by Hansheng Shao and Srini Devadas, and Hansheng is given the talk. Go ahead.
For introduction, yeah. Hi everyone, my name is Hansheng, and this is John work with my advisor Srini Devadas, which is also here, and Srini will help me to answer any tricky questions. And as you can tell from the title, the key problem we want to solve here is like we're trying to build a fully automatic framework, privacy analysis framework for any given possibly black box, right, data processing. We want this framework can tell us, right, how can we privatize or randomize it until it can produce satisfied privacy guarantee. Okay, so before we start, we want to ask a general question. So what is security? So one simple and intuitive answer is, okay, adversary cannot recover your secret. But if we take a closer look, actually, this definition is incomplete, right? So on one hand, we didn't specify the power of adversary. In particular, we didn't specify any assumptions on the adversary's prior knowledge, right? So in the extreme cases, the adversary already knows your secret. So no matter what kind of encryption function you want to use, right? So he can always like recover your secret. On the other hand, right, finally, we still use some mathematical language to describe this inference harness. But before we can talk about any concrete results, right, so we need to specify what kind of inference task we try to prevent, right? We don't want the adversary to recover like any bit of your secret, or like don't want to recover any membership of your input set. And moreover, we define some measurement of the harness. Like one option is like can be like we give some upper bound of this posterior success rate that the adversary can complete this kind of inference task. Okay, so with this basic understanding, we can give you some basic model or general model of this information leakage. We have some secret X, we have some processing function M, right? And we're going to release, or our leakage is captured by the MX, the output. So M capture many applications. For example, you have sensitive data. I train a neural network out of your data, right? The neural network, this train out is the output. And in some side channel applications, right, MX may capture like your traffic network and like the memory patterns when I send some messages or get access to some files in the cloud. So most existing classic security definitions actually rooted in the input independent indistinguishability, or like also called like adversarial worst case indistinguishability, right? So this is a framework which doesn't like directly answer the inference harness problem, but gives a very clear and smart way and an alternative to describe the security, right? The security defined as, okay, no matter what the prior belief the adversary has, right? After he observes this additional release, it doesn't change his belief a lot or doesn't provide too much additional information. So this framework basically can be summarized as 4 steps. First step, right, we need to determine the privacy concern, which type or feature like we try to protect. Then in different privacy, we'll try to protect the individual data, right? In crypto, usually we will protect the entire set. Second step, we'll select some proper semantic divergence phi to measure the difference between, right, the likelihood functions. Third step, we will define some general concept of the adjacent data set, right? They only differ in the sensitive feature we try to protect. So for in different privacy, adjacent data means like 2 data sets differ in 1 data point. And the last step, we need to quantify the security. So how secure your mechanism is, right? So it's like we need to worry about like the worst case or the largest divergence between the 2 likelihood functions produced by 2 adjacent data set X and X prime. And this upper bound, like captured by this epsilon, will be our privacy parameter. Okay, so input independent privacy actually is widely applicable, and we don't need to worry too much about the priors, but it also has several challenges. First thing here is like, actually the security proof is very hard. Like for example, when we write a different private paper or like a crypto paper, the most challenging part is like we really prove the proposed mechanism is really secure, right? Especially in different privacy, we need to show, okay, we add this amount of noise and this amount of noise can produce the claim like epsilon delta DP parameters, right? Unfortunately, in the worst case, this is NP hard. The other issue here is the generalization to more general inference task, or like, for example, reconstruction error, right, or reconstruction attack. This kind of implication or the relationship is not clear. How can we use the indistinguishability results to generate that? Third issue here is like, actually, even if there exists an oracle, which can tell us what is the optimal, what are the ideal perturbations, right? Minimal noise we need to perturb your mechanisms, right? Many lower bounds have told us, right? So the utility loss must be very huge, right? So for example, in different privacy, this is known as a curse of dimensionality. I want to release a d-dimensional vector, right? The noise of scale is proportional to the dimension d, right? So that is why, like in current applications of privacy preserving deep learning, right, we must pay for a large utility loss. Okay, so now we can talk about what is packet privacy. So packet privacy basically is the instance-based privacy. So the instance-based is referred to as, right, we will assume the entropy or the underlying data distribution. Our motivation are twofold. First, we want packet privacy to directly answer the fundamental inference hardness problem. So for example, like as we said, before we can give any concrete results, we must specify the priors. Second issue here is we also want to build a fully automatic framework, right? So given like we already know the general impossibilities of NP hardness, right? So we need some additional something to avoid that. Okay, so what exactly we want from packet privacy? So we want like given arbitrary adversary prior knowledge or data distribution, right? For an arbitrary inference task and for an arbitrary possibly black box data processing, right? We want to show there exists some framework and tell us how to perturb it, how to randomize until it can produce satisfied privacy guarantees captured by, we give you some upper bound of the posterior success rates of the adversary. To give you more intuition, right? So we can describe the workflow here. So once your data distribution is given or entropy is given, right? Combined with your selected inference task of interest, these two together determine the optimal A prior success rate before the adversary observe any additional release, right? And then combined with additional leakage, right? It then determine what the optimal posterior success rate will be. And this is something we try to control. Okay, we need a bit more mathematical notations to for our definitions. First, we will use X delta to represent the adversary's guessing on your sacred X. We will introduce an abstract success criterion rho, which equals 1 if and only if, okay, adversary returns unsatisfied estimation. Third issue here, we will use delta O as the minimum or the optimal A prior fair rate before the adversary observe your release. And the delta captures the minimal posterior fair property. And then usually in crypto, right, the difference between delta O and the delta, it will be the posterior advantage. Usually we expect to be negligible. Okay, so now we can give you a formal definition of packet privacy. First, we explain why we call it packet privacy, right? So we basically borrow the packet learning language, like to formalize this security problem as the adversary cannot effectively learn anything meaningful from your release. So we only use this language to describe this hardness, but we actually don't use the techniques of packet learning because we prove impossibility results. So the definition is actually straightforward, right? So for a mechanism M, right, given some distribution D for your selected success criterion, right, we call M satisfy packet privacy. It means the following experiment like is impossible, which modeled as like a game between the user and the adversary, right? So user generates your secret encoded by M sent to the adversary. Adversary is asked to return an estimation, right? And we want to ensure he cannot return a satisfied estimation with a high chance 1 minus delta. Okay. So given like we have discussed, right? So given data distribution your priors and the selected like the inference task, these two already together determine the optimal A prior rate. right? So it's equivalent to considering what the posterior advantage is, right? Here we introduce a more general definitions of this posterior advantage. So we consider two Bernoulli variables, one of parameter delta, one of parameter delta O, right? We can use an arbitrary F divergence to measure these two Bernoulli distributions. And we will show why this is more general and how to control it. So this is our main theorems. It's very, actually, I should say it's clean and summarized in words. It's basically say the F divergence measure the posterior advantage is upper bounded by the F divergence between the joint distribution of your input X and output MX to the distribution of the cross product between the marginal distribution of your input X and the distribution of W. So W is an arbitrary random variable just on the same output domain of your mechanism M. In particular, if we select the F divergence to be KO divergence and the W to be your distribution of W to be the output distribution, then what do we get? We get the KO divergence based posterior advantage is bounded, upper bounded by the well-known mutual information. There are several remarks here. First, the right-hand side is independent of the row. This suggests like, right? So the selection of your inference task only influence the left-hand side, what the optimal A prior success will be. Also, if we select the F divergence to be total variation, this just reduced to the standard posterior advantage, right? The difference between delta O and delta. Also, because the right-hand side, right, is independent of your row. So once we can give an upper bound of the right-hand side, it suggests like we actually provide a uniform upper bound for arbitrary posterior advantage for any selections of your row here. And also this assumption, this theorem doesn't require any like additional assumption on your data distribution and your output distribution, right? So basically, the data generation can also be a black box. So now I can give you a short summary and a comparison between data independent privacy and pack privacy. As we mentioned, right, so data independent privacy, whether applicable and we don't need to worry too much about the priors. Also has a challenge to hard to generate the proof, unclear about the generation to explain an arbitrary inference task. And also the privacy, like a trade-off is really loose, right, requiring large noise. As for pack privacy, first, it's still a worst case guarantee. The worst case means like it's resistant to arbitrary adversary strategy. But it's instant-based because we assume the data entropy here. But as a good news here is when we produce the privacy analysis, the privacy analysis can also like benefit from the data entropy, as we will show in the next example. Second thing, now we are able to build automatic privacy analysis. Third thing here is like, as we propose pack privacy just to directly answer the inference hardness. So this suggests like, right, it has a very clear interpretation. Fourth thing, and very important is like pack privacy can produce very tight utility privacy trade-off. And it's not restricted by the curse of dimensionality as we show, like when we release a large dimension release, right? So the noise signal can be O1 in many practical applications. Okay, so before we talk about the automatic privacy and framework, right, we give you a simple example, like how can we exploit the data entropy. So for example, in this simple example, right, we consider the mean estimation of Gaussian data. In this case, both your input distribution and output distribution has a closed form. So in this case, right, when we average out n Gaussian data, right, actually the upper bound of the mutual information can be bounded by log 1 plus 1 over n. So in other words, when we average out more Gaussian data, we accumulate more entropy, right? And this random estimation itself already able to hide any individual among this population without any noise. So this is very different from different privacy, right? So if you need some meaningful privacy guarantee, we need to randomize your noise for some deterministic processing function. Okay, but unfortunately, in practice, most of our processing is very complicated, and we don't have a clear picture on either the output distribution or so we need an automatic privacy analysis for the black box processing. So in this case, we need to add some noise. So why? But the motivation is pretty different from different privacy. The problem is we don't have a clear picture on what the output distribution looks like. It's a black box, right? We need to add some continuous noise to enforce the noise output to follow some good shape. For example, when we add some Gaussian noise, it just means, right, your output distribution will become captured by a Gaussian mixture model. And what we want here is we don't want any mess. We don't want to do any algorithmic analysis for your processing function, or you don't want to do any modifications to the processing function. We just want this automatic protocol tell us, okay, how much noise we need to add until we can produce our required privacy guarantee. Okay, so the following theorems gives us, okay, what the upper bound of the mutual information looks like. So this upper bound only requires the knowledge of the covariance matrix of your output distribution, MX. And we show, okay, once you can always select the proper noise large enough, right, to ensure this upper bound is close to 0. And more importantly, this theorem actually shows what is the optimal noise you need to produce a fixed mutual information upper bound. So actually, this noise scale, the multiple noise scale, is determined by the sum of the square root of the eigenvalue. So in other words, you can imagine if your output distribution is largely concentrated in a low rank space. So basically, we can add just O1 noise, right, to give you a very strong packet privacy. To give you more intuition, right? So let's just describe what the black box analysis framework is, right? So because first we have to have no idea of your output distribution looks like. We will sample MIID data from the distribution D. We evaluate them and compute the empirical covariance and also the eigenvector and eigenvalue. So this MIID data, basically big data, just help us to understand what the simple statistic of your output distribution looks like. And the interpretations of this eigenvalue and eigenvector just like, so the eigenvalue means your output distribution project along that direction and how much the noise, how much the power is, right? With a larger eigenvalue, this suggests like the variance along that direction is larger. The second step is, okay, after sufficient many simulations, okay, we are confident about what the covariance looks like. And then we can confident to release our data. We will sample a fresh data, okay, X from the D again, and we will add an isotropic noise. So this is why we only add necessary noise to your output, is because like the anisotropic noise, right? The variance of the noise along each direction captured by your eigenvectors, right? It's only proportion to the eigenvalue, right? So if your power is larger, okay, I need more noise. But if your power is less, right, I mean, even now need noise to hide that. The last step is very simple. You just add this noise to your output, and then we can show you can already satisfy packet privacy guarantee. Okay, so there are several remarks here. So first, how large is the simulation complexity is. So if you really want to get the optimal Gaussian, like the Gaussian noise, there is OD here. The D is because we need to estimate like the power along each direction in the D-dimensional space, right? So in this case, there is the OD. But in our paper, we present several tricks there, like there are many trade-offs there. So for example, you can always use a larger noise to compensate for your more restricted simulation budget, or like for even higher confidence bound. Also, you can also alternatively to use some looser but efficient estimation. If you only focus on like some L2 norm thing, right? So in this case, your estimation is simpler, and you only need to with 0.1 time complexity. But as still the trade-off, you still need to pay for a larger noise because your noise estimation is looser. Okay, so there are also many further generalizations in our papers. For example, packet privacy enjoys straightforward composition, and currently we focus on like the entire data set security. So if you have a particular focus on the individuals, right, actually we have stronger results for that. Moreover, in the distributed case, right, we can also generate the centralized packet privacy to the local privacy, similar to the local DP, right? These details can be found in our paper. And finally, we want to show you some concrete examples, like how can we use packet privacy to address the practical applications. So as I will say, right, currently we are already allowed to do end-to-end privacy analysis. So one example, like why not we just consider the deep learning, right? We train a neural network out of a data pool, let's say M-minist, right? And how we ensure our data X enjoying the entropy, right? We constantly randomly sample a subset of this set, like for example, 35K, right, out of them. And we train a neural network out of them. So this suggests like if we achieve packet privacy in this setup, it means even if the adversaries know the universe of your training set, right? For a particular model I train out, you can still now identify what exactly my training data is applied to train this model. Okay, and still, this is we take the entire deep learning algorithms as a black box, right? We don't need to add any modifications to the algorithms, and like surprisingly, right? So actually, your neural network actually concentrated in a relatively small low rank space, right? And for this large dimension release, actually we only need a constant noise. The noise is about 4, right? To ensure a very strong packet privacy for an upper bound smaller than 1, right? And we only need to pay a small utility loss, right, for it. The other issue is we can also converse about the unsupervised learning, right? We have a set and a set of data, right? We try to split it into k subsets, and we try to estimate the mean of each subset and use it for the clustering. So still, k-means is still like a non-convex problem, and we will still take the k-means algorithms as a black box without any modifications. Okay, the following table just to tell you, like, we still do the similar thing, right? We run the k-means algorithms on an n subset of the data pool from the n list, right? And we consider different tasks, k run from 2 to 10. So on one hand, you can observe like with a larger n, right? It means with more data is enrolled in this data processings, and the algorithms becomes more robust, right? Because you're closer to the population statistics. On the other hand, right, when the k increase, it means the data processing becomes more complicated, right? And it becomes less robust, and you need a larger noise for that. Oops. Okay, so following now we can conclude this work. So first, we believe packet privacy is a new framework that allows us to use many new tools to understand the the black box processing and the black box randomness. For example, currently there are many heuristic data obfuscations, right? Those randomness cannot be explained or characterized by the input independent security, for example, the instant head or mirror crypto, right? They fail to produce the strong, worst case independent, input independent guarantee. But now packet privacy give you can probably to quantify the privacy amplifications from this kind of randomness. The second issue here is like packet privacy is our like a first attempt to build a automatic privacy analysis framework. Okay, so of course, like currently we assume like the data distribution is known, or like we can simulate your data generator. But there will be a very interesting question, like in the regime of input independent privacy or security definition, that whether we can still do this automatic privacy analysis, right? So in this case, given that the general NP hard impossibilities, right, we need to find some meaningful assumptions to avoid that. And also you can view that now packet privacy now enables researchers in robust statistics and the privacy to benefit each other. When your processing function is more robust and or your estimation is more efficient, it means you can more efficiently with less simulation complexity to obtain your privacy proof. And on the other hand, when your algorithms processing function is more robust, it naturally implies strong privacy guarantee. Okay, so that is I want to talk, and happy to take any questions. Thank you.
Questions for Hanshan?
Hi, thank you for the talk. I was trying to think about how this could go wrong. And I was thinking maybe in practice, is it that you really need to understand your input distribution well? Because when you sample in order to get these estimates, like if it's like biased, then might you run into trouble? Or is this, I guess, robust a bit to this might be an ignorant question, sorry, but yeah.
Yeah, very interesting question. Actually, so first, if you only worry about the posterior advantage, so I don't know what my priors is similar to the input independent case, right? In this case, once this data generator is a black box, you can simulatable, okay? That's only assumption. Then you can still quantify the posterior advantage. That part is independent of what your priors is. But if you really want to know what the A prior success rate is, right? So you first need to know the A prior posterior success rate, right? You first need to know what your A prior success rate is. So in this case, no matter if your distribution is biased or what, but you first need to specify what the distribution is to determine your A prior success rate, right? Before you can talk about the posterior success rate.
Okay, thank you.
Hey, Hanshan, thanks for your talk. And I wonder, like, sorry, maybe this question is real stupid, but I wonder how does it affect your like privatization mechanism when your targeted attack is different? For example, will the mechanism be different if we're targeting reconstruction attack or membership inference attack?
So that is captured by that rule, right? You still
Right.
remember there's a success. This is a very abstract success criterion. So rho equals 1 if and only if the adversary produced a satisfied estimation. So if you want L2 norm like smaller than 1, this is reconstruction attack, right? So it basically means, okay, like the X theta produced by the adversary compared to your true secret X should be smaller than 1 when rho becomes 1. So this will determine the a prior success rate on the left-hand side in our bound.
Oh,
So rho is arbitrary thing. You can set arbitrary inference task. Once this, you can determine what the rho looks like, and then you can get that corresponding inference task advantages.
okay, thank you.
Quick question.
Thanks for talk. So, from my understanding, it quite resemble the local sensitivity in differential privacy in assuming, and when we join the samples from a data distribution, you actually join samples from the samples joined from the data distribution. So the true underlying data distribution ground truth is actually intractable to both the data owner or the adversary. Is my understanding correct? Or
Actually, this is a very good question. So, but smooth sensitivity is some attempt we try to do some instance-based analysis in differential privacy. But the smooth sensitivity is still the worst case guarantee. Actually, the smooth sensitivity is still NP hard to compute if there's some proof there. So actually, yeah. Anyway, so we can use smooth sensitivity, but still the bound itself is NP hard. And yeah, so currently we can only use smooth sensitivity to compute some like median applications or what. It's still limited, right? So for general case, it still will be restricted by the NP hardness impossibility result. So yeah, so that's why I'm thinking about like whether we can generalize this result to the input independent case, like how we build this automatic privacy.
All right, let's thank Hanshin again. And last talk of the session. Title is One-Way Functions and the Hardness of Probabilistic Time-Bounded Kolmogorov Complexity with respect to sampleable distributions by Yanni Liu and Raphael Paz, and Yanni is giving the talk.
Yeah, thank you for your introduction. And hi everyone, my name is Yan Yi, and today I'm very excited to be here to give the talk. And this is a joint work with Professor Raphael Paz at Cornell Tech and Tel Aviv University. And all right, today, so let me start with something that's really controversial. Well, we are cryptographers, and we know we use a lot of assumptions in cryptography. So I'm going to ask, well, what is the best assumption in cryptography? Well, you might say we have like fractional assumptions, the discrete logarithm assumptions. They are amazing assumptions. But we know if we have like quantum computers, then how about like LWE, it's like post-quantum secure? Well, that is the problems. Or if you were at the best paper talk, then you know having structure is sometimes not like a good thing. Well, you might say, well, like how about the existence of one functions? Or even more, just NP is not equal to P, which is often referred to as, well, the holy grail of cryptography. Okay, today, since we are in a music hall, right? So I'm going to show you like something very like romantic. So I'm trying to argue that, well, the best assumption that we can build cryptography from is the assumption that the science is hard, while implementing scientists' discovery in polynomial time is hard. Okay, hold on. Let me not to explain like what do I mean by science hard, but just think about it like morally, right? We are all scientists and we're doing science every day. So we should really believe and we really know that science is hard, right? So okay, if you're willing to believe that and together with a bunch of other things, today I'm going to show you how to build cryptography from that. And today our focus is one function. So let me start by introducing the notion of one function. So one function, well, as you guys all know, like is a notion proposed by Diffie and Hellman in '76. And if a function f is one way, it's easy to compute. So and it's hard to invert. So given like a random x, it's easy to compute f of x, but it's hard to go back to x from f of x. And we all know that when a function is really like the most central object in cryptography, and it is both necessary and sufficient for basically the whole world of a private key primitives. So whether when a function exists is the unequivocally most important problem in cryptography. Well, and we know that a very recent work by Liu and Pass, we showed a characterization of when a function. So we showed that when a function exists if and only if, well, this a time-bounded Kolmogorov compass problem is hard on average. As we will see very soon, this like Kolmogorov compass problem is really a classic problem even in computer science and has been studied since the 60s. But before I introduce the notion of Kolmogorov compassity, let me, kind of take another perspective to look at this result. So this is saying like either when a function exists or the time-bounded Kolmogorov compassity problem is easy on average, meaning like an algorithm like deciding Kolmogorov compassity of strings. This is actually like efficient algorithm for optimal file compression, for inductive reasoning, and even for like optimal machine learning. Oh, great. It's like amazing. There's kind of like much more you can do. But this like one caveat that the algorithm we get from LP20 only works over uniform random strings. Okay, you can compress like file like in an optimal way. That's very cool. But well, who cares about compressing uniform random strings, right? So today I'm going to show you that, well, actually we can have a better algorithm that works over practical instances. And this is going to have, well, amazing consequence. Well, we can show that if there's no one function, then science is easy over real world data. Okay, let me first introduce the notion of Kolmogorov compassity. And this is a notion proposed by Solomonov, Kolmogorov, and Chartin. And it's actually inspired by like the following question. Well, I have like two strings there, and I ask like which of the following is more random. Well, apparently like the first string is like not very random, but the second string seems to be. But I want to like notice you that they all have like the same probability weights under uniform distribution. So it's suggested by Kolmogorov. So let's instead look at, well, the length of the shortest program that outputs this string x, and we'll let k of x denote this quantity. And this k of x turns out to be like amazing measurements of how random a fixed individual string is. And of course, we can make it formal by fixing universal Turing machine U. So in this talk, just think about U as being Python, and we are looking for, say, the length of the shortest program that's input like a description of machine M together with input type W, and such that when being simulated on U, M together with W will output the string X. And this notion has a lot of amazing applications, such as you can prove like Gödel's incomplete theorem, you can prove like density of primes, but unfortunately it's uncomputable. And uncomputable things are typically not very interesting in computer science. So let's instead look at, well, the time-bounded variance of this notion. And imagine that there's like a random time-bound T, and we're restricting ourselves within like all programs that determinates within T of n steps. So we can define the notion KT, well, which is like roughly the same thing with an additional requirements that your program determines in time T of length of x. And if you think about it, well, it becomes computable by a brute force search. And it's actually in MP if T is a polynomial. So the question here is, well, can KT be efficiently computed when T is a polynomial? And as mentioned, this is a problem that has been studied in the Soviet Union since the 60s, and also independently by Hartmanis, Sipser, and Co. in the 80s. And it's closely related to the MCSP problem, minimal circuit size problem. And you can see in MCSP, like the computational model is like circuits, but here we're interested in Turing machines. And this is often referred to as a meta-complexity problem. So we are interested in, well, the complexity of computing the KT complexity of the string. So it's like meta-complexity. Well, this is really what people should do in metaverse. Okay, so let me introduce the notion of average case hardness that we rely on. And somewhat intriguingly, this problem was also studied in the 60s. And they refer to it as a frequential version of the problem. So they ask, well, does there exist an algorithm that computes KT of x? Well, just for a large fraction of x. So imagine that there are like 2 to the n strings there, like n bit string, and can you get an algorithm that computes, say, 1/2 of fraction of them? And a simple observation, also made in the 60s, is that KT can be actually, if you're okay with like an approximation version instead of computing it exactly, then it can be approximate within an additive factor of log n with very decent probability, well, y minus 1 over n. And the approximation algorithm is very simple, just output n, which is the length of the string. Well, if you think about it, there are just that many like short programs, and each of them produce like a single string. And therefore, most strings will have like really high KT complexity. And of course, we can ask like a more general version of this question. Well, given some like efficient sampleable distribution D instead of the uniform distribution, do we have like an efficient algorithm that computes KT over strings that are drawn from the distribution? And now I'm ready to introduce like the hardness condition that we need. So we say that KT is mildly hard on average with respect to some distribution D if there exists a polynomial P such that no PPT heuristic H can compute KT of X with the probability 1 minus 1 over P for strings that are sampled from D for infinite many n. All right, this is what we need. So let us look at our main theorem. So our main theorem says, well, let us consider a probabilistic variance of KT denoted by PKT, and I will introduce this notion very soon. And the following are equivalents. So first, when functions exist. And second, there exists some sample distribution D under which PKT is mildly hard on average. And third, this also holds over the uniform distribution. Well, so let me introduce PKT. It's a recently introduced notion. And it actually captures what happens to KT if you have access to a common random string. So typically here, the goal is kind of, hey, give me a CRS. I'm looking for the shortest program, kind of output the string with access to the CRS. And you can think about it as the same as KT up to like a factor of log n under standard derandomization assumption. So let's just think of it the same as KT for now and look at our main theorem and what does it tell us? Well, so if we look at the implication that 2 implies 1, this actually yards like a strong and natural win-win situation. So what does this say? So we know that then this is saying that either 1 is true, namely when functions exist, or 2 is not true, namely for any efficient sample of X, we can with high probability find the shortest program that outputs the string X. Well, this is not quite true because like morally 2 is like a decisional problem, but here we need like a search version of it, but we will show that it kind of follows our proof. So if we have a search algorithm that kind of looking for the shortest program, this is actually like an efficient approach implementing ideas behind Occam's razor. And as mentioned before, and let me be a poetic here. So this is going to have amazing consequence. So we're going to show that either one function exists, or science is easy if you believe in Occam's razor. Okay, which is well the most popular and prevailing principle in our science community today. So what is Occam's razor? It's kind of saying that well the simplest explanation is mostly likely the truest. Well, so say you have like a bunch of hypotheses kind of explains the same observation. Which one do you want to believe? Well, you probably would like to believe the simplest one. Okay, so suppose you believe in Occam's razor, and we have an algorithm kind of finds the shortest program for you. So how do you do science? Well, you collect a bunch of data and you run the algorithm. The algorithm will output some program, shortest program, that outputs the data. Well, this is actually what we're looking for if we believe in Occam's razor. Of course, there are some caveats. We need to assume, well, nature is efficient and collecting data is easy. And but I do want to mention that you can make this formal, make this like a romantic story formal by as did by Solomonov in his like inductive inference theory. But I'm not going to talk about this here. So let me go back to our main theorem. So there's like more things happening there. So if we look at the implication that 2 implies 3, which basically says, well, if some distribution under which this problem is hard, then it is hard over uniform distribution. This is actually like an intriguing statement of this problem. Like we get like a uniform is the hardest distribution. And additionally, we want to mention that our theorem also holds with respect to the standard notion of KT by assuming a derandomization assumption, namely E does not have infinite often non-deterministic size 2 to the 0.01 n circuits. which is used to argue that MA equals MP. Okay, so let me mention some related work. There's a recent work by Elango, Stanton, and Ren. They show that, well, under the randomization assumption, infinite open one function is equivalent to KT being hard to omega log n approximate with respect to some sample distribution. Well, but here we only require hardness of solving the exact computing problem. And as we have seen before, it's like approximation version and computer version is like quite different. And in fact, any distribution under which KT is hard to be omega log n approximates itself, this distribution itself is a one function. So their result doesn't show like new insights into how can we build a one function from scratch. All right, so let me take a look at our proof. So today we're interested in proving the implication that 2 implies 1. So namely, assume there's like a sample distribution under which PKT is hard, and then we want to show that one function exists. And for simplicity, we're just going to consider KTs or without the CRS, the standard notion in this proof overview. And so let me define like a kind of an important notion that we'll be using in the proof. So we say that a distribution D is, well, like a polynomially bounded by the complexity measure KT. If D samples any string with probability, well, that's at most a polynomial times 1 over 2 to the KT of X. So if you think about it, this is like saying we do not assign too much weight to any string that is KT random. So if you have like a really high KT complexity, then I'm going to sample you with like a really small probability. And for those who are familiar with the LP20, so our proof kind of proceeds as in the following 2 steps. So step 1, we're going to show that the LP21 function will be still weakly one way if we switch the uniform distribution to any distribution that is polynomially bounded by KT. And in step 2, we'll show that any efficient sample distribution must be polynomially bounded by KT. Well, not quite. Either we need like a CRS or we need like a derandomization assumption. And so today, for those who are not very familiar with LP20, I will sketch you the proof behind step 1. And we want to remark here that step 2 follows from the coding theorem of Lou, Oliveira, and Siemens. And we also have like a independent proof, which is like a much more elementary. So let's look at step 1. So here our goal is, well, construct a one function. So first observation, that's observe that LP20 only gives you a weak one function. And we know that a weak one by the hardness amplification lemma, we know that a weak one function implies a one function. So let's say it suffices to just construct a weak one function, and let us look at the construction. So first we let C be a constant such that for any string X, KT complex X of X is at most length of X plus C. So if you look at Python, you can output any string with like, and you put your string there. So C is just length of command print, which is just 5. Okay, C is a constant, and we define the function to take like a random input pi prime, which of length say n plus C, and another index of length log n plus C. And it proceeds as follows. First, here's like my very long string pi prime, and I truncate it to the first I bit. And I interpret the first I bit as a program and run it for like T of n steps. And finally, we output, well, my index I and together with my output Y. Okay, so we claim, well, just like taking a random string, truncate it, and run it as a program and output your outputs together with the index. That's like my one function. So if you look at this, you say like, well, hold on. If we just look at Python programs, well, if you just sample a random program, there's like a decent probability that this program just invalid and it's just output boss. So why is this one way? Well, we are only going to show that this is a weakly one way. So we are okay with, you know, like some inputs that are kind of not the functions that are not one way on it. Well, so let's look, it's become, hopefully this is becoming more convincing. And let's look at, well, the reduction. Suppose that we have like somebody who inverts this function. And now we want to use this inverter to get, well, to compute like KT complexity of strings that are sampled from D. So like how does a heuristic proceed? Well, we first take like a random string Y that is sampled from D. We're going to try all possible index, well, from 1 to 3 all the way to n plus C. And for each index, we're going to run the inverter on the output like I together with Y. And if my inverter succeeds, it will return me a program of size I such that if you run the program, it will output Y, but it doesn't always succeed. So you need to like verify this. And finally, we just simply output the smallest index on which this check pass. Or if you're looking for a search problem, search algorithm, you just output the program itself. Well, like intuitively, you will think, well, if kind of this inverter program, this like heuristic should work. But I would like to point out this like a serious issue here. That's here, like our heuristic algorithm H is fitting the inverter A the wrong distribution over Y's. Well, here like Y is distributed over D, which is like a sum distribution. However, this is like nothing to do with D in our one function constructions. So this is like usually like a serious problem when you're trying to construct the one function. And our solution here, well, is to use like a relative distance arguments in LP20. We can show that they are not too far away from each other, and our heuristic here actually works. And we get like a algorithm that computes KT with like descent probability, which is a contradiction. All right, so let me wrap up. So today we have seen that the following are equivalent. So first, when functions exist. And second, there exists some sample distribution under which PKT is mildly hard on average. And third, on the uniform distribution, PKT is mildly hard on average. And as mentioned, this is going to have a very like a poetic win-win situation. Either crypto exists or scientific discovery is easy. Okay, you might say, oh, like I don't believe in Occam's razor. Like we are doing science. This is not rigorous. Okay, here is like something for you if you don't believe in Occam's razor. And our approach actually our work actually provides an approach towards excluding the passive land. So the goal here is to base one function on MPs are hard on average. And we show that this implication boils down to proving MP completeness of this PKT problem. And I won't go into detail because I don't have like enough time. So I will end here and thank you for listening.
Any hard questions for Yanni?
All right, then seems everybody is happy with Occam's razor. Nice.
All right, so since we're in foundation sessions, I should point out that I think the clear mistakes in the Latin spelling of your Occam razors should be praeter necessitatum at the end. And it's attributed to Aristotle, who had this criticism about Plato's splitting two worlds and stuff. This just show it off my knowledge of the classics.
Yes, I agree. Then let's work towards excluding pestilent, right? So let's base my functions on MPs out hard on average. Yes, great.
All right. We are off to lunch and we'll reconvene at 2 p.m. Thanks everybody.